Welcome to the start of a new unit. We're going to be looking at patterns in this unit, uh, different types of patterns and rules for patterns. We're going to start generic in this lesson. This is going to come from chapter 12 in section 1. Targets for today: I can write the first n terms for a given sequence. I can write a rule or equation for a given pattern. We're also going to look at, this lesson might be split over 2 days. We'll do all the notes today, but it might be split over 2 days. You're going to write a sequence in summation notation, and you're also going to use summation notation to find the sum of a given series. Okay, what is a sequence? Sequence is a function with a domain of consecutive numbers. Sequences can be finite, 2, 4, 6, 8, starting at 2, ending at 8, going up by 2s, or infinite, 2, 4, 6, 8. When you see the dot, dot, dot after 8, that just indicates the pattern continues on forever and ever, or sometimes they'll say it'll continue on to and then have an ending spot. So this one, the way it's written, indicates that it's going to go on forever and ever. Okay, the domain is the position of the terms. First term, second term, third term, fourth term. The range is the actual terms, or what you see in the pattern. So the first term, its domain is 1, but the output is 2, or the first term is 2, the second term is 4. That's what a sub 2 means. The a sub 3 is 6, the third term, which is 6. A sub 4, that's the fourth term, which is 8. Okay, so sequences will be defined by rules. F of n equals 2 times n, or a sub n equals 2 times n. And just for your information, FYI, series are sequences that are added together. So if I said find the series, or for this, the sum of the series, 2, 4, 6, 8 would get added together. Okay, so let's write the first 6 terms of the sequence in graph. So let's say we have an equation like this: a sub n equals 3n minus 2. To write the first 6 terms, what we're going to do is we make a table with 1, 2, 3, 4, 5, and 6 as the input values, and we make an output table, or y, or a sub n in this case, and we would plug in those numbers to get the outputs. So we plug in 1, we get out 1. We plug in 2, we get out 4. Because 3 times 2 is 6, minus 2 is 4. 3 times 3 is 9, minus 2 is 7. 3 times 4 is 12, minus 2 is 10. 5 times 3 is 15, minus 2 is 13. And you can see how it goes. And we have the work down here. We can plot those points on a scatter plot if we wanted to. You could also go to y equals on your graphing calculator and go to the table and do that as well. Okay, we've done that enough at this point. You should know how to do that, or if not, then you need to get a refresher in class. Okay, here's another one. Write the first 6 terms of the sequence in graph: 2 to the n plus n. 1, 2, 3, 4, 5, 6, and then we just plug the numbers in and we get the first 6 outputs. 2 to the first power plus 1 is 3. 2 to the second power plus 2 is 6. And we can see how it goes, and we can see the curve pattern here. Looks like it's going almost exponentially. Okay, so now here's the fun part. Describe the pattern, write the next term, and write a rule for the nth term. So basically what we're going to be doing is we're going to be looking at these patterns of numbers, and we're going to try and find a rule for it. Now what I like to do is I like to make an XY table, or an input-output table, and see if I can see a pattern. So we'll call this X and Y. You can also think of it as N or an A sub N. And we have 1, 2, 3, 4. We're going to just look at A right now. Okay? 1, 2, 3, 4 terms. So 1, 2, 3, 4 that we see so far. And we know that when we plug in 1, we get out negative 1. When we plug in 2, we get out negative 8. When we plug in 3, we get out negative 27. And when we plug in 4, we get out negative 64. So any predictions on what the next term is going to be? What are we going to get when we plug in 5? Right? What are we going to get? Well, I kind of like to figure out what is the pattern here. And if we looked and ignore the negative signs, if you take 2 to the third power, that's 8. 3 to the third power, that's 27. 4 to the third power is 64. But they're all negative. So my guess is that the next term is going to be, well, 5 to the third power, but negative, or negative 125. That's my guess of what I think the next term is going to be. So what is the rule of describing? So basically what are we doing? We're to describe it, we are cubing the x, or the n input, and making it negative. We're cubing it and making it negative. In other words, we're cubing it, you think of order of operations, and making it negative. We're cubing 2 and making it negative. We're cubing 3 and making it negative. So can we come up with a general, cubing 4, making it negative? How do we turn that into a rule? Well, if we take these numbers that are changing, if we look on the left side, the things that stay the same are negative and the cube. The thing that changes are the numbers that we input. So that when we come up with a rule for this, it's a sub n equals, well, the things that stay the same, they're going to stay in there. The negative and the cube. The things that are different, that's where the variable goes. A sub n to the negative n cubed. That's our rule. So we describe the pattern and write out what I described, but basically it was cubing the input and making it negative. That's how we can describe it. Okay? Let's look at part B, or B. 0, 2, 6, and 12. So for B, it's 0, 2, 6, and 12. So, same thing, I always start out this way. We're not told what type of pattern this is. We make an XY input table, or an A sub n table. So, we plug in, our first we have 1, 2, 3, 4 terms again. So we're going to predict what the fifth term is, also what the next term is. The first term is 0, the second term is 2, the third term is 6, the fourth term is 12. Well, what seems to be happening here? Well, it looks like it went up by 2, looks like it went up by 4, looks like it went up by 6 to me. So my prediction is it's going to go up by 8 again, which would mean 20. So my prediction that the A sub 5 is 20. The fifth term is 20. Okay, so we're starting at 0, and we're increasing by 2 more each time. That's kind of what we're doing. So how do we figure this out? How do we describe this pattern? Well, plug in 1 somehow. I'm going to put it in parentheses. And somehow I get it to be 0. Well, in order to get it to be 0 from 1, I'm going to have to multiply it by 0 or add a negative 1. So we'll see what we do here. Let's look at the second term. 2 and 2. Well, to multiply to get 2, we're going to have to multiply by 1, or we're going to have to add 0. 3. We're going to get out, what, 6? So we would multiply by 2, or we have to add 3. So let's look at this. Let's try the multiplying. We're multiplying by 0. Actually, we'll do the adding one first. Okay? We add negative, oops. Take 1, we add negative 1 to it, that makes 0. And 2, we'd have to add 0. 3, we'd have to add 3. That doesn't really look like a pattern in red to me. So I don't think it's adding over and over again. Let's go with our other assumption that it had to be multiplied. Multiply by 0, multiply by 1, multiply by 2. Well, I think I see something here. 4. I would multiply that by 3, and I would get to 12. And if I plug in 5, and I multiply that by 4, it gives me 20. So I think we're onto something here. There seems to be a repeating pattern of in order to get the next answer, the next output. How do we put this into words, and then how do we put it into an equation? Well, it looks like to me that we're taking the input and we're multiplying it by the number one less than the input. So we're taking integer values, we're inputting them, and we're getting out values that are one less than what we plugged in. So how do we do that in MathStreet? Well, if we look, if this is our original input, the 1, 2, 3, 4, 5 in green, if we say that's n, or x, or whatever you want it to be, well, how does this value in blue relate to it? The value in blue is 1 less than it, so it would be n minus 1. Would then give us our equation for the function. So a sub n equals n times n minus 1, or if we distribute that, we could get a sub n equals n squared minus n. Okay? So there is our equation, our rule. We described it. It was the input multiplied by the input before it, and that's how we do it. Okay, we're going to switch gears here, and we're going to talk about finite and infinite series. Finite series are a series of terms being added together with a start and an end. Infinite series, you keep adding numbers forever and ever and ever. Okay? We're going to focus mostly on sums of finite series in here. Just so you know, there are higher levels of math where you'll look at infinite sums and pre-calc and beyond. But right now we're going to primarily focus on the finite sums of series. Okay, so find the sum of a series. So what does this mean? Here is this Greek letter. If you look in the type black, sigma looks like an E almost. Okay, but it's a capital sigma. It stands for summation sign. You might have noticed it from my green mathlete shirt that I've worn from time to time. It's the summation sign, sigma. So when you see that, you know that we're going to be adding some terms up. Okay, so to the right here in blue, that's the rule for the terms. 2 minus 3k, that's a rule or model or equation, whatever you want to call it. That's how we're going to get our outputs. At the bottom, k equals, in this case, it's whatever letter is in the model or the rule. In this case, it's k equals 3 because we use a 2 minus 3k in the rule. That's our starting term. A lot of times we'll start at 1 or 0, but then you can start wherever you want in a summation notation. The number at the top is the ending term. So what this means is that the summation of k equals 3 to 5 of 2 minus 3k, that is just the third term plus the fourth term plus the fifth term. A sub 3 plus a sub 4 plus a sub 5. Now you can do this by hand, and you can say, okay, 2 minus 3 times 3, which is negative 7. 2 minus 3 times 4, which is negative 10. And 2 minus 3 times 5, which is negative 13. And then you would add those all up. Negative 7 plus negative 10 plus negative 13, and you would get negative 30. Now, lucky for you, your calculator has all this fun stuff on there for you. So if we go in here, we'll write these steps down. We go to alpha, and you hit window. The second one down is summation notation. So we can plug this all in. We're always going to use x. We're going to start at 3. Go on our up bar, we're going to go up to 5. In our rule, instead of 2 minus 3x, we're saying 2 minus 3. So 2 minus 3k, we're going to use 2 minus 3x. We hit enter. We hit negative 30. So you can do that on your calculator. Let's write those steps down so you can have them in your notes. 1, we're going to hit alpha, the green button. 2, window, the green button at the top. And then we're going to select number 2 for summation notation. And 4, just a reminder, use x every time. right here, if you want to pause this and copy these special formulas down, you may. I'm not going to go through each of them because we have a graphing calculator. The graphing calculator, I just showed you that method, can prove these or find these sums. But if you know you have special situations and you don't have a graphing calculator, these formulas might be useful. So have them in your notes and see if any of the problems match up when you're home practicing with these. Okay, so go back and forth, pause it, write those down. I'm going to move ahead and catch up with you when you're ready. Okay, so now we're going to kind of bring it all together here in this problem, and it's going to say write the series using summation notation. Now, if they give you a rule, that's great. But you notice if they give you something like this, we don't have a rule. We're going to have to come up with a rule on our own. What we do know is we do know that the first term, second term, and third term are 25, 50, and 75. We know some term down here has an output of 250. So if we can find the rule, we can then kind of use it to find out, okay, what is that nth term that gives us 250? So it should be a sub n at the top. Okay, so let's see what's happening here. It looks like we're adding 25 each time. Looks good to me. So the rule for me, we input 1, I get out 25. I input 2, I get out 50. I input 3, I get out 75. So what are we doing to go up? If we're adding 25 over and over again, that means 25 times 1, 25 times 2, 25 times 3. So our rule appears to be a sub n equals 25 times n. So if we're going to write this in summation notation, we have this part, 25n. So we start at n equals 1, that's our starting value. We just have to know where we end up at. The way we do that with this type of situations, we say, okay, well, 250, that's our last term. So 250 equals 25n. Let's divide both sides by 25. And 250 divided by 25 tells us that the nth term for this series is 10. So 10 is going to go on the top. We've just written that in series notation. Do one more real quick. Let's go down to C here. The other one is very similar. It looks like in this one we're adding by 1 each time. We're starting at 5 and we're adding 1 each time. That's kind of what it looks like, doesn't it? 1, 2, 3, and we don't know, we end up with 12. And at this point we have x, we do x, y, a table. Plug in 1, get out 5. Plug in 2, get out 6. Plug in 3, get out 7. Plug in some number, we get 12. So, got to come up with a rule for this one, don't we? We plug in 1, we plug in 2, we plug in 3. We do something to it, we get 5, we get 6, we get 7. Well, it looks like there's a constant difference. So that tells us that it's going up by 1 each time, but we don't want to add 1 to 1, it's not going to give us 5. So if I add 4 to 1, I get 5. If I add 4 to 2, I get 6. If I add 4 to 3, I get 7. And look at this, it looks like x plus 4 equals 5. Well, if we're going to write that in summation notation, we'd probably use n, I or j, we'll use n. That looks like n plus 4 equals a sub n. So to write this in summation notation, we would say n equals 1. We always start with the first term. N plus 1, we're writing these anyways. We have to find the last term though. We know the last term is 12, but what is it? Well, what we do is we do like on the last one, we put 12 in for the y or the a sub n, and we solve. Oops, subtract, not 8. There. Subtract 4 from both sides. The nth term is 8. So in our summation notation, up here it's 8. And we have just written that observation. So going back and reviewing our targets for today, I think we addressed both days. Like I said, you're most likely a 2-day assignment, but now you have the notes for both. So we're good to go in class, whether it's 1 or 2-day assignment tomorrow, either way. The notes ready to be checked tomorrow, and we'll see you then.